Okay, well, thank you so much for having me here and for the lovely introduction. I almost forgot what I got and when it happened. Yeah, it's great to be here, and thank you for taking time from your revision. I know how everybody's busy now. On the way here, the smoke was coming out of Vatican, but there won't be any smoke today. I don't have the demonstration here to show you how superconductors actually really work. But I'm going to tell you about a few aspects that we learn on our journey in understanding the magic world of superconductors. So the title of my talk about mapping the electronic phases actually refers to how we look at materials which conduct electricity in momentum space. So we look at Fermi surface, how they are organized, and what they tell us about the electrons inside the materials. I'll start with a brief introduction on superconductivity for those who are not familiar, just to give you a flavor why do we care about them and how important they could be for future technologies. Okay, so let me start. So here it's a phase diagram that I'm going to describe later. This is a Fermi surface map of an ion-based superconductor, and this is a simulation about how quantum oscillations occur. So the history of superconductivity started when scientists, more than 100 years ago now, they were developing new tools to be able to understand matter. And this was Camille Onnes in Leiden. He was the first person who liquefied helium and set up the first cryogenics laboratory in the world. So this gave him new opportunities to try to understand things about matter, and in particular, one question he was trying to address was what happened to electrons when we cooled a material down to very, very low temperatures. And there were various predictions. So here we have resistance versus temperature, and the various prediction given by Lord Kelvin was saying that when we cool things down, resistivity normally goes down in a metal because the vibration with the lattice will slow down, so electrons will not scatter all the time. But eventually, Kelvin suggested that electrons will freeze out, so the resistance will just keep going up. Dewar thought, oh, surely if there is no more interaction with the lattice, there won't be any more resistance, and the resistance of the material will go towards zero. Mathiasen, however, said, well, any material has defects, so eventually the resistance of a material will decrease, but it will saturate to a value given by the concentration of impurities we might have in every system. And to address this, Onnes thought, okay, having all these ideas, I should get something very clean, a very clean material. He went to gather pure samples of mercury, and he went to measure resistivity versus temperature. And he found out on 8th of April 1911 that the resistance of pure mercury actually dropped down to absolute zero. He obviously had to check, verify that it wasn't an experimental error, some broken contacts, some other unwanted effects. And eventually he was convinced that that's the real thing. So none of these predictions were true, and a new state of matter was discovered, and superconductivity was realized. Besides having zero resistance, actually superconductors have lots of other interesting properties which are less commonly known. A superconductor normally expels a magnetic field. So here is a superconducting system above a magnet. These are the flux lines are expel. So if this will be a type 1 superconductor, all the flux lines are completely expel, and the system will be a perfect diamagnet. So there will be B field inside the superconductor will be zero. For type 2 superconductors, however, they allow some flux lines to penetrate through the system, and this is called flux spinning. And this is what allows the levitation to occur, because we pin this flux line to the track then the superconductor will expel the magnetic field and eventually levitates. So when this expulsion happens, actually surface currents will be set up, which will cancel out the applied magnetic field. So that's why the total field will be zero inside of a superconductor. Another interesting aspect about superconductor is if you would have a ring or a hollow superconductor and you cool this down in a magnetic field, you can trap magnetic flux. And as a result, you create persistent currents in a loop. And interestingly, those type of fluxes are quantized. So you can use such a system, a ring, to be able to count the number of fluxes in the material. So they are used as very sensitive devices. And if you have a superconductor, insulator superconductor, a junction, a superconductor will have a wave function with a phase, which will change across the junction. And as a result, there will be a spontaneous current which occurs due to the phase differences between the two sides of the superconductor. So this is called Josephson effect, which was predicted here in Cambridge a long time ago. If you were to apply a voltage to this Josephson junction, then you will generate a frequency. And this is the way how the unit of volt is measured. So when we think about application for superconductors, because they have zero resistance, they also have a very large critical current. So they allow very large critical currents to pass through them before the superconducting phase is destroyed. Critical currents can be enhanced by increasing the pinning factors in the material, something which I'm not going to touch upon. But just to give you an example, a superconductor niobium thin wire, which is used to construct lots of superconducting magnets, for example, has critical currents of 10 to the 9 amps per meter square, compared with copper wires, which is more than a factor 100. And you can see here in the picture the difference in also the quantity of material, how much copper cables you will need to produce the same amount of currents compared with a piece of superconductor. So they are extremely space efficient, they allow large currents, and having a wire with large currents, you can construct very strong magnets. And you can construct strong magnets and very compact, which will have lots of applications. And if you set up such a magnet in a persistent mode, because if you have a closed loop, you can do that. If you only have a superconducting circuit, then that current can flow forever. So imagine you could create a magnet, you seal it in a cryostat, and you can just have that magnet for a very, very long time, kind of 10 to the 5 years or so. And here I want to show you that a superconductor is characterized by its critical parameters, so it's the critical temperature. Unfortunately, many of them only superconduct at low temperatures. By its critical current density, so above a certain value, you will destroy the superconducting state. And obviously, the critical magnetic field. So above a certain value of a magnetic field, you will destroy the superconducting state. So among many applications, here are a few which come from all these important properties superconductors have. As I said, obviously levitation is used in levitating train, maglev, which can travel to speeds of above 500 kilometers an hour. Obviously we will have power cables which will be very efficient. In this case, they still need nitrogen cooling because TC of this material is still not high enough for room temperature applications. MRI magnets are used as superconducting magnets, create the MRI magnets, and they are set up in this persistent mode, such that you don't need to fill up the magnet every time, every day, to keep it in the superconducting state. So we can imagine a world where if we find a room temperature superconductor, we could create MRI magnets for our own use at home. So if you break a finger or something, you can just scan it and find out what has happened. Having strong magnets are considered for electrical planes, for generation of energy in tokamak to confine the plasma. They are already used for particle accelerators. The Josephson junction are used in quantum computers. These are the little squids, which allows this flux quantization to detect very small magnetic moments. And obviously, magnetic fields are also used for research. And this is one part I'm going to talk about, how we use magnetic fields to study other superconductors. So where we are in the history of superconductivity started with ONES more than 100 years ago. Lots of new materials have been discovered, and the transition temperature, the critical temperature, kept going up. So initially, there were this superconductor called conventional superconductors. And then in 1986, we have the family of cuprate superconductors, the red line, which took the transition temperature above 150 Kelvin. Over the last 10 years or so, systems very close to room temperature have been discovered. They are unfortunately only working at very high pressure, so in a very confined environment, in a pressure cell at 190 gigapascal. That's very close to the core of the Earth. This is how much pressure one has to generate. And in 2008, we have the discovery of ion-based superconductors. This is the systems I'm going to talk about, in particular the ion selenium, which in a monolayer form can reach temperature close to 100 Kelvin. In the last 2-3 years, we have a new family that's of nickelates, and reports of a transition temperature of about 80 Kelvin have been reported under pressure. So scientists try hard and hard to find out new combinations, now also using machine learning approaches to identify potential new systems that they will work towards higher and higher temperatures such that we can unleash the huge range of applications superconductors could have. Just now how we understand superconductivity. In 1957, three theoretical scientists, Bardeen, Schrieffer, and Cooper, developed the BCS theory based on their initials, which describe how a superconductor actually works. So they made prediction about how the transition temperature is determined and gave us this formula. So KBTC being related to h bar omega d, which is the Debye frequency, so it's the vibration of the lattice. And here an exponential decay term, minus 1 over lambda, and lambda is the coupling between the electrons and phonons. So this will be the vibration of the lattice. The term depends on the density of states and this effective interaction between electrons and the lattice. So what they said, superconductivity occurs due to pairing of electrons. And how this pairing occurs is kind of illustrated in this animation. Imagine you have a system at zero temperature. All ions will not move because there is no thermal energy. But if you have an electron passing through the lattice, which has a negative charge compared with the ions, which are positive, that electron will slightly distort the environment and bring the ions closer towards this electron. And if another electron comes and passes through exactly the same path, it feels that retarded interaction from the movement of the ions. And that's what we call electron-phonon coupling, because over a certain distance, those two electrons have a coherence. So they feel this attractive interaction, which is over the size of, this is the coherence length. So that will be how far they are to feel the interaction from the same ion environment. So it's an exchange of phonons. So interaction, electron-phonon coupling is that in exchange with the lattice vibrations, because the lattice interacts and the second electron feels that interaction. So what this results that the charges determined from experiments were found to be 2e. That means we have electron pairs. And when superconductivity occurs, these pairs gain energy by pairing up, and given by this expression, so it's still determined that by the Debye energy and e to the 1 over lambda. And when all the electrons are condensed in pairs, this is the, we have all the largest gap opens between this pair state, which is a condensed microscopic state described by a single wave function with an amplitude and a phase. So this is the description of conventional superconductivity, which tells us that a superconductor, inside of a superconductor, we form Cooper pairs due to interaction with the lattice. So now in how we think in the momentum space about electrons, we know that for a metal, all the states will be occupied in momentum space with spin up and down, and the surface which separates occupied from unoccupied states is called the Fermi surface. In terms of what happens in a superconductor, the states which will participate in pairing are those which have a certain energy away from the chemical potential, so within a shell of energy equal to the h omega d, which is the Debye energy. So these are the electrons which are in the vicinity of the Fermi level, which feel this interaction and lead to the pairing of electrons. And when pairing occurs, electron which spins up and spin down will pair up. So this will be a pair with opposite spin and opposite momentum. So L equals 0 and S equals 0 state. And all the other electrons then will form pairs. And inside the superconducting state, we'll have continuous scattering between one pair into another pair to maintain this coherent state. So that's how the process occurs. And now let's me introduce you the family of superconductors we've been working over the last few years, which is supposed to be one of the simpler ones because there are two elements, iron and selenium. Yeah, if we understand the simplest one, probably we could understand the rest of them. So structurally, these materials form, it's a tetragonal system. So you have a square lattice, in-place square lattice of ions, and then you will bond to those ions different elements from the chalcogen group here. We have selenium, sulfur, or tellurium. What was quite unusual about this family of compounds was that finding superconductivity when you have iron wasn't expected. Iron is quite magnetic in general. You create magnets out of iron. So, and superconductors in general do not like strong magnets because the superconductivity is destroyed. So yeah, it was not at all predicted that this could occur, and it seems like it's possible, and it's not just these materials, but there is a huge family of different combinations of elements while still maintaining this two-dimensional planes of iron. So once you have this iron layer coordinated in the tetrahedral environment, you create superconductivity for different combinations of different elements. So looking at how superconductivity occurs here, so this is the temperature axis, and here we have tellurium substitution, so changing the composition on this side, or sulfur substitution, the same here. So instead of selenium, we put sulfur, or instead of selenium, we put tellurium. And the other axis is pressure, apply pressure to the system. And the pink region is superconductivity. And looking at this phase diagram, we see that superconductivity can occur in various places, and it has a very unusual behavior. Sometimes it's suppressed, sometimes seems to be enhanced. Nearby to the superconducting phases, there are other phases, and there isn't a well-defined recipe why this happens. I mean, if we think about chemistry, we might think, okay, if we put a tellurium ion, maybe we change the lattice, so some things will be suppressed in a linear way, but in reality, things are very, very complicated. And this is what we call that the systems are very strongly correlated. They emerge, superconductivity emerges from other competing phases. In this case, we have nematic electronic phases. This will be an equivalent electronic of organization that you might find in liquid crystals, where you break the fold-fold rotational symmetry of the lattice, and it becomes very anisotropic. And under pressure, one can stabilize also a magnetic type of organization, which is called a spin density wave, where the spin polarization will vary in the system. And this seems to be that when we have that kind of phase superconductivity, it's much more enhanced. So I will show you some data from using sulfur substitution to look at our Fermi surfaces, or combining sulfur and selenium, and also some of the tellurium systems as well. And to do all these studies, one needs to have access to very, very clean materials. This is a picture of I would say almost perfect single crystals of an iron selenium sulfur, which has very nice edge, and it shows this tetragonal symmetry. Another thing about iron selenium, so these are all bulk materials. They are single crystal. One can grow them in the lab using a technique called chemical vapor transport. But another spectacular aspect of iron selenium is that when it's grown in a single layer, so this using MBE techniques or some other thin grow technique on strontium titanate, it creates superconductivity at much larger transition temperature. So this, in this regime, this is the type of material where you have a single layer of iron selenium, and underneath you have strontium titanate. And you can see TC now is going from about 50, 60 Kelvin towards 70 or even higher. And one can also dope the materials. So what I show you in the substitutional graph earlier, selenium, tellurium, and sulfur are in the same periodic group. So if you exchange them, you do not add extra electrons. You just change the sizes. But you can add other elements that can dope the system, or you can intercalate between them. You can put some potassium in, and then you can enhance superconductivity by giving the system lots and lots of electrons. And as a result, these pictures here are slices of Fermi surfaces. The one I'm going to talk about today will be looking like this, which has a hole-like pocket in the center, electron-like pocket in the corner. But if you dope with electrons, you are going to increase the size of electron pockets, and the size of the hole pockets will decrease. So that's why you have no more red pocket here. So this is the effect of the electron doping. So when we look at these new materials, which cannot be described by the conventional BCS theory, which I showed you earlier, that the Cooper pairing and superconductivity occurs due to electron-phonon coupling, we need to try to look at all the aspects and understand each component which contributes to the pairing. So first of all, we need to understand how electrons interact. So, and this we're going to see is via their effective masses. So if you have a free electron, through your lattice, usually you expect a mass of an electron. Obviously, the band structure is going to change what masses that you might extract. But in many of the systems, the masses are extremely heavy. You can have effective mass of 4 or 10. And this occurs because the electrons interact among themselves. And if they interact, maybe some of those interactions will also help with the pairing. Sometimes those interactions may be bad for the pairing. But this is one aspect of our research. We try to understand in which conditions and which phases help the pairing, and what type of features of the Fermi surfaces can enable that the pairing exists. So one can pair up for a single Fermi surfaces. For example, this is the hole pocket. You can pair up like in the normal BCS superconductor, but you can pair up with a different momentum vector, which introducing some new components which could be driven, for example, by magnetic interactions. So this is now reflecting this. In a conventional superconductor, you form Cooper pairs because the effective interaction between electrons and phonons and the Debye energy scale is very important. Whereas in many unconventional superconductors, you could have the mediation and the pair formation could be driven by interaction with the spins. And the magnetic susceptibility then become important, and it has lots of properties which depends on the details of the Fermi surfaces and potential instability towards magnetic instabilities. So now I'm going to describe one of the techniques that we are going to use, we have used already in our research, which is angle-resolved photoemission spectroscopy, or short ARPES. And experiments we've done are the diamond light source very close to Oxford. In a photoemission experiment, what we have light, which can be polarized light, shining over a very clean, fresh surface, and then you detect, due to the photoelectrical effect, you detect the emitted electrons, which are captured in this analyzer, and due to the conservation of energy and in-plane momentum, will give access to the binding energy of the electron in the material. And we can determine how the electronic band structure looks like, and how their momentum dependence looks like, and visualize Fermi surfaces. Here, this is the diagram of the whole process, how it happens. So in ARPES experiment, one will measure only occupied states. Often you have to know the work function of the material, and then you can determine how the binding energy versus momentum looks like for the sample that you measure. The intensity that you extract in this type of experiments will depend on various factors. Depends on the coupling between the light and the type of orbitals present in your material. So that's called the matrix element effect. It will depend on the Fermi-Dirac distribution. Often the experiments we do are at a very low temperature to be able to see very sharp bands, and also on the spectral function of electron and the type of excitations they have. So here I have a picture from an experiment, which is a Fermi surface map. It shows the hole pockets here, electron pockets in the corner. Over here is the second Brillouin zone. So this is the first Brillouin zone of the material. And the difference between the two pictures is that we use different light polarization. Here is the linear vertically polarized light. Here is linearly horizontal polarized light. And because the bands have different orbital characters, let me go back here. If if I go around of an electron pocket, I can see that the color changes. What that means, it means that the band formation involves different orbitals. So if it's dark blue here, it's an XY type of orbital. If it's light blue, XZ, or purple, YZ. And the light couple in different way to this orbital, and this is why different lights will give us slightly different pictures because of this interaction and the matrix element effects, which influences the data. So now this is how we measure and what we get from experiments. This is the binding energy versus momentum, and it shows the band dispersions, hole-like pockets for this type of light polarization at the high symmetry points for our material. So this is the Brillouin zone. These are band structure calculations that we can do. It shows that you have a multi-band Fermi surfaces composed of 4 different pockets. So you have the red one, hole-like, the little green one is also hole-like, and also only present around the Z point. And then we have 2 electron pockets at the corner of the Brillouin zone. So when you measure in ARPES, one can focus on the high symmetry point, and you do a cut like this, and this is the result of that cut. By changing the energy in an experiment, one can probe a different high symmetry points. So you can go at the top of the Brillouin zone at the Z point here, or the center of the Brillouin zone at the K point. And having the data to understand about the material and about all these interactions which are important for superconductivity, we would do the calculation. So this is a calculation of the band structure. This is only using density functional theory. And we calculate binding energy versus momentum. It shows that they should be 3 whole bands crossing the Fermi level. Here is the gamma point, but Z point is very similar. And when we compare with the data, we can estimate the degree of real normalization of these bands. And what's unusual in these materials is when you do this comparison, you find out that the degree of renormalization is quite different depending on the orbital character of the bands. So it can be 3, 2, or actually 8 or 9 for the DXY band, which is the dark blue, the most renormalized band. And we call this orbitally dependent mass renormalization. And what it means that electrons inside the materials, they are not just correlated, but they also seem to remember the orbital character from which they emerge. That means also for superconductivity, all these aspects need to be taken into account. And one can do the same measurements, focus now on the electron pocket, and here you can see the occupied states only. So you see, you only measure in ARPES the occupied states. The 2-band dispersion there are originating from this type of behavior, and then you have kind of hole-like dispersion over there. But there are some saddle points and the general points at the high symmetry points, which I'm not going to talk more about now. So I mentioned about the nematic electronic phases these materials have, and they are, again, an electronic organization of the system, and the way they manifest in experiment is shown in this picture. So this is now a map of iron selenium, but a low temperature inside the nematic phase. If in the tetragonal phase we could see over here fall-force symmetry for all the pockets, when we go at low temperature inside the nematic phase, we see that this symmetry is broken. And now the system have 2-fold symmetry. The pockets have elongated, the electron pockets along one direction, and the hole pockets in another direction. So these are the manifestation now of this nematic electronic phase. It induces significant anisotropy in the Fermi surfaces, and as a result is going to influence all the properties that we measure. including the superconducting gap which emerges in the system. So because the Fermi surface has distorted, the gap will be extremely anisotropic, both on the hole pocket and on the electron pocket inside the superconducting phase. And over here is the measurement of the hole coefficient. Some of you might be familiar. When you want to know the number of carriers, you will do a hole measurement, you cool down your system, and you get your number. In semiconductors, you learn there are different regimes. In the systems, we have many bands. We have electrons and holes. They are compensated metals, meaning the number of electrons and holes are often the same. But the hole coefficient can become very unusual because we introduce this nematic electronic phases, and the scattering can become very anisotropic itself. So you don't have a single type of scattering time. The scattering itself can be different along different directions. And that's the hole coefficient here for single crystals of iron selenium, and then we have created flakes, so kind of two-dimensional devices, and the hole coefficient has changed significantly when the system has become 2D. In another type of ARPES experiment, we were looking at the evolution of the electronic structure in the phase diagram when we replace selenium with tellurium. So in this particular case, the nematic phase is suppressed with tellurium substitution, and superconductivity becomes enhanced just outside the nematic phase. So we could follow the behavior of the different bands. And one aspect which we found quite unusual was that the band which was the most correlated one, the one with DXY character, the blue band here, was very low inside the nematic phase, but was shifting towards the Fermi level exactly when the superconductivity was getting enhanced. So our suggestion in this report was that it looks like now superconductivity will have another pairing channel which might boost the transition temperature here. The effective mass of this band also increases significantly, so strong correlation. The availability of new states for pairing seem to all contribute to enhance the superconductivity when we use tellurium as a substitution. Okay, and now I'll move towards the high magnetic field studies that we do. This is another way to understand and to access Fermi surfaces. So high magnetic fields can be created in different ways. This is a superconducting magnet that we have in Oxford, up to 16 Tesla. One can generate DC fields towards 45 Tesla to different facilities around the world in Europe or USA. And even larger magnetic fields can be generated for very few milliseconds, up to 90 Tesla, at different pulse field facilities around the world. This is an example from Toulouse, where we often travel to do our experiments. So in a magnetic field, how we get information about Fermi surfaces, it comes from the fact that you have to consider the Landau quantization of the energy levels. So for a normal metal, you have a Fermi surface and all the states will be occupied inside there. But when you turn on a magnetic field, then for the direction normal to apply magnetic field, all the states will be quantized by this expression. And the energy will be h bar omega c, which is the cyclotron energy, omega c being EB over the cyclotron mass. So as a result, then the density of states will look like have all the spikes, similar to what you might expect for a one-dimensional system, because the in-plane direction now is quantized. And if you were to vary a magnetic field, you will vary the density of states significantly. So in a quantum oscillation experiment, this is the simulation, all these circles are Landau tubes, and the red circle is the chemical potential. So as you increase the magnetic field, Landau tubes pop through the chemical potential and lead to oscillations in the density of states. And Onsager has shown that actually the frequency of these oscillations are directly related to the cross-section area on the Fermi surface, normal to this applied field. So in this picture, I have, again, our multi-band Fermi surface. And if my magnetic field is along the z direction, or kz direction, then I would expect to have different cross-section areas. So I have a minimum and maximum for each of the cylinder. So let's say beta pocket, chi pocket, delta pocket. So this is just for the whole pockets. And then for the other pockets, I'll also have 2 frequency for each cylinder because I measure extremal areas for each of them. So the Fermi surface and the response in quantum oscillation can be very complicated if you have lots and lots of contribution from all these different extremal areas. The different techniques that we use to measure quantum oscillations are shown here. If we have very tiny crystals, like only about 50 microns or so, then we can use torque magnetometry in high fields. These are obviously transfer measurements, making a whole bar with solder contacts. The crystals are below 500 microns, so this is quite a complex job. This is exfoliating the single crystal and creating devices and then using lithography to make all the connections. And another cute technique that we use, especially under applied pressure, it's called tunnel diode oscillator technique. You wrap around a coil, around your sample, and this becomes an inductor in an LC circuit. You have a tunnel diode in that circuit which you bias in a negative resistance part of this circuit, and effectively you create a resonance of this LC circuit. And by measuring resonance, you can see the changes in the properties of your material, including the observation of quantum oscillations. And all these experiments are possible if the crystals are very, very clean. So before you even start doing any measurements, you want to check your materials. You want to have very clean X-rays to be sure that you are going to be successful, because any impurities will affect the Landau level separations and will lead to broadening of the Landau levels, means you won't see any quantum oscillations at all. And here's some examples of how they look like. So we are dealing with superconductors. That means they have zero resistance. We need extremely high magnetic fields to kill the superconductivity and then to access the normal state in the vicinity where superconductivity occurs. And very low temperatures, which is about here, 0.4 Kelvin, at fields of 45 Tesla, then we can start seeing this very weak oscillatory signal. One can subtract a background to be able just to quantify the oscillations. And then those oscillations will be periodic in 1/b, and we Fourier transform the signal, and those are exactly the cross-section areas of the Fermi surface of our material. This is another example now measuring the different components, ρxx and ρxy, in pulse fields up to 90 Tesla, and we can, even the quantum oscillation spectrum seems to be dominated by different parts of the Fermi surface. You see the oscillations are stronger here, some of them compare with the other one. And in quantum oscillations compare with ARPAs, where you know exactly the positions of the bands, the high symmetry points. In quantum oscillations, we only extract these cross-section areas. We don't know for sure where they come from. So to be able to assign them their origin, one is to do very detailed angular dependence study, first of all, to be able to work out the shape of the Fermi surfaces we measure. And this is an example here how we rotate our sample in magnetic field and how we look at the cross-section areas, minimum and maximum, how they vary as a function of this orientation. And then in this particular case, we also have the ARPES data. The energy dependence show us how the shape of this whole pocket looks like, which was in a very good agreement with what we got from quantum oscillations. And what we found from this study was that the sizes of these Fermi surfaces are extremely small compared to what the band structure predicts. And this is another manifestation of this very strong correlation I was talking about, meaning that the electrons in the system interact so strongly and the Coulomb interaction are relevant. The interband interaction, meaning interaction between the hole and electron pockets, are extremely large, and they cause this shrinking of the Fermi surface. And this is another manifestation of why these materials are not easy to understand, because just doing a calculation is not enough to what happens in reality. One has to do the measurements to be able to work things out. Another route of measuring quantum oscillations is using pressure. So if you have a pressure cell, you have a single system, and by changing the pressure of the system, you can go across different phases. And you can really see the phases where superconductivity is suppressed, the phases where superconductivity is enhanced, and then that also gives you access to a huge variety of information about the link between the competing phases and superconductivity, and also how the correlation will vary. Here's an example of a phase diagram constructed under applied pressure. So we took a system, iron selenium with 11% sulfur. We measure resistivity in this case. So these are all the resistivity curves as a function of temperature. They are shifted vertically, so they are all superconducting. And the anomaly here is this is where the nematic phase occurs. It has a very strong anomaly. And then as we apply pressure, we suppress the nematic phase. Superconductivity has a little dome here. But if we keep pressurizing, then superconductivity is enhanced. And this is another phase compared with the phase which occurs out of the nematic phase. It seems like we are dealing with changes in the character of the superconductivity just by tuning via applied pressure. And here are some experiments of quantum oscillations under pressure for a different system, which is when we are right on the border of the nematic phase, we have a very slow oscillation dominating the signal. But then we enter the tetragonal phase, we have quite a rich oscillatory signal, and they slowly move to the right, means the Fermi surface keeps expanding. All these cross-section areas keep growing as we increase the pressure. And they all come from the different cross-section areas that I described a bit earlier. And if we look at the temperature effects, here it shows the complexity of seeing this quantum oscillation and how fragile they are to maintain the condition that the cyclotron frequency to be larger than kBt and omega theta much larger than 1 means we need very clean system, very low temperatures, very high magnetic fields to be able to visualize them. And here is 0.35 Kelvin. By the time we are at 1.5 Kelvin, the amplitude of the oscillation has died out and they are all gone. And from this information about how the system varies with temperature, actually we can access, it gives us access to the quasi-particle effective masses. So this is the Fermi-Dirac distribution, and these are the lambda levels. at finite temperatures, then the Fermi-Dirac distribution becomes very broad. And as a result, the amplitude of the quantum oscillations will vary significantly with temperature. And from this variation with temperature, for each pocket, then we can extract the effective mass of the quasi-particle, which is the orbitally average mass for that particular pocket. And the changes in effective masses, the fact that they are enhanced, is due to both electron-electron interaction and electron-phonon interaction. And this gives us a feeling, quite detailed information, which electrons are more correlated and how we can detect precisely their effective masses. So the summary of some of the findings we had for a system under pressure are here. So this is the material where we suppress the nematic phase, and we went to higher pressure and we saw the superconductivity is enhanced. This is the dome of superconductivity in 8 Tesla. We call this superconducting 1, and this is the dome for the superconducting 2. And the blue dots are the effective masses that we extract from quantum oscillations. And what we learn from here is that the superconducting emerging out of the nematic phase, it's a very strongly correlated state, and it seems to follow the behavior of TC. So that means the correlations which lead to mass enhancement must be responsible for the superconducting state itself. Whereas at high pressure, the effective masses for this particular pocket, which is the delta pocket, is the whole pocket in the center of the Brillouin zone. The effective mass is kind of almost flat. It's not changing that much with temperature, whereas the transition temperature, which are the triangle, is enhanced almost a factor 3. So either these electrons do not participate in superconductivity, or the type of correlations that give rise to, which give the light effective mass are not involved at all in the superconducting pairing. And this also tells us that we are dealing with very clearly with 2 different types of superconducting phases tuned by applied pressure. And probably I might need to stop now. Just briefly go through. Here we can also study the effect of impurities. The way you look into that, you look at how the amplitude varies with applied magnetic field, and you can quantify the scattering times of the electrons for each of these pockets. And knowing information about the Fermi surfaces are relevant for understanding the upper critical fields. So upper critical field is the magnetic field at which superconductivity is destroyed. Here is the analysis of the 2 different directions, so applying magnetic fields along the c-axis or perpendicular on the c-axis. We could then use the information from the Fermi surfaces to try to work out what type of couplings contribute to the pairing in this material. And the coherence length is given, it can be extracted directly from upper critical fields, and they are of the order of about 10 nanometer at very low temperature. So this is the size of the Cooper pair in the system. Similarly, we found a remarkable superconductor called calcium-potassium ion 4 arsenide 4 with upper critical field towards 190 Tesla, which has potential for lots of applications which only require, let's say, 20 Tesla or more. But yeah, this was very exciting. And applied pressure eventually can also kill superconductivity. In this study, we used diamond anvil cells. We kept the prime pressure. Superconductivity was enhanced up to here in this green regime. But above 6.2 gigapascal, which is 62 kilobar, we noticed that the resistivity is not 0 anymore, and it becomes finite, and the system almost looks like becomes insulating. And that led us to conclude that There must be some other factor which now kills superconductivity at very high pressure, either the way the applied pressure acts, the pressure medium inside, or there is another transition which is kind of enhanced due to the presence of this uniaxial effects. And that's why superconductivity is killed. Initially becomes filamentary, like different pockets still superconducting, but in the end, it's completely lost. So this is my summary. Ion-based superconductors are a very exciting platform to understand unconventional superconductivity because they give us access to lots of different parameters and tuning parameters to really explore the fundamental behavior of the quasi-particles of the Fermi surfaces, which are essentially for understanding the pairing. Different tools obviously give us different insight on the behavior of these materials, and in our group we have developed quite a large range of tools to allow us to do this. Obviously we use angular resolved photoemission spectroscopy, which works very well at ambient pressure. It works very well if the samples can be cleaved and you have very shiny surfaces. But quantum oscillation gives additional access to in extreme conditions where no other technique can go. You can tune by pressure, and within a single sample, you can really explore very rich phase diagram. And obviously, these are very relevant for understanding why superconductivity occurs. Just to show you that for those interested, we are part of a center for doctoral training in superconductivity. So any of you considering PhD next year, please look into this. So it's between Bristol, Oxford, and Cambridge. And these are some images of the students in our lab. So thank you very much for your attention.